Hello. Hello and welcome to this video. In this video, we will solve 10 more interesting problems on polynomials and quadratic equations. So we will start from problem 381 and go till problem 390. So if you have not watched my previous videos, we repeat the ritual. If you want this PDF, which I'm showing here, you can go to my website www.astavoka.org and click on this second link, a variable in algebra, and the PDF will be downloaded. So I will give the link in the description, so don't worry about it. You can simply click the link in the description and the PDF will be downloaded. So with that out of the way, let's get started. And as always, I will say that when I am reading the problem, you should pause the video, and only if you cannot solve the problem yourself, look at the solution. So without further ado, let's get started. Question 381 says that if a into p plus q whole square plus 2pbq plus c is equal to 0 and a into p plus r whole square plus 2bpr plus c is equal to 0, then show that qr is equal to p square plus c by a. So if you look at the equation, a into p plus x whole square plus 2bpx plus c is equal to 0, then q and r will be root of this, because if you replace q by x here and r by x over here, then this equation will come. So this equation, we expand the first term and it becomes x square plus 2 into a plus b into px plus c plus ap square is equal to 0. Now product of roots is given by qr is equal to ap square plus c by a, which is equal to p square plus c by a. Question 382 says that if alpha beta are the roots of the equation x square minus p into x plus 1 minus c is equal to 0, show that alpha plus 1 into beta plus 1 is equal to 1 minus c. Hence prove that alpha square plus 2 alpha plus 1 by alpha square plus 2 alpha plus c plus beta square plus 2 beta plus 1 divided by beta square plus 2 beta plus c is equal to 1. So we rewrite the equation as x square minus px minus p plus c. So since alpha beta are the roots of the equation, we can write alpha plus beta is equal to p and alpha beta is equal to minus of p plus c. Now we compute alpha plus 1 into beta plus 1, which will be alpha beta plus beta plus 1. And we substitute for alpha plus beta and alpha beta, we get minus p minus c plus p plus 1, which is equal to 1 minus c. So that is what was required for alpha plus 1 and beta plus 1 over here. Now once we have done that, we look at the given expression, that is this one, left hand side of that. So it is alpha square plus 2 alpha plus 1 by alpha square plus 2 alpha plus c. So the numerator is alpha plus 1 whole square. And in the denominator, we add and subtract 1. So it becomes alpha plus 1 whole square minus 1 minus c. And similarly, the other term becomes beta plus 1 whole square divided by beta plus 1 whole square minus 1 minus c. So what we do is we write 1 minus c as alpha plus 1 into beta plus 1. So these two terms are that. Once we have that, we can write the entire stuff as alpha plus 1 whole square by alpha plus 1 into alpha minus beta plus beta plus 1 whole square by beta plus 1 into beta minus alpha. Now see what happens is alpha plus 1 will get cancelled here and beta plus 1 will get cancelled here. So it will become alpha plus 1 by alpha minus beta plus beta plus 1 divided by beta minus alpha. So it will be, we will have to take a negative sign here to make this alpha minus beta so that our denominator becomes equal. And once that happens, 1 will get cancelled and the numerator will also become alpha minus beta, and that is equal to 1. And that's how we prove question 382. Question 383 says that if alpha beta be the roots of the equation x square plus px plus q is equal to 0 and x to the power 2n plus p to the power n x to the power n plus q to the power n is equal to 0, where n is an even integer, prove that alpha by beta and beta by alpha are the roots of the equation x to the power n plus 1 plus x plus 1 to the power n is equal to 0. So alpha beta are the roots of the equation x square plus px plus q is equal to 0. So alpha plus beta is minus p and alpha beta is q. Now it is given that we have x to the power 2n and p to the power n, x to the power n plus q to the power n is equal to 0, and alpha beta are the roots of the 0. So we substitute alpha beta and we find that alpha to the power n, beta to the power n are the roots of the equation y square plus p to the power n y plus q to the power n is equal to 0. So you see that instead of that you think that y is equal to x to the power n here. And so alpha beta are the roots here. So it will be alpha to the power 2n. Okay, so if it becomes y square, then alpha to the power n will be a root of this. Now once we have this equation, we can say that alpha to the power n plus beta to the power n is equal to minus p to the power n. And because n is even number, okay, so n was even. So this will be positive, but it should be negative. All right, we'll see this, okay. So now alpha to the power n, beta to the power n is equal to q to the power n, which implies that alpha plus beta to the power n is equal to minus p to the power n is equal to p to the power n because n is even. Okay, so why this has become equal to this is it is actually alpha plus beta to the power n, not alpha to the power n, beta to the power n. So we have alpha plus beta is equal to minus p. Okay, so alpha plus beta to the power n will be minus p to the power n, that is this much. Now what we have to find is x to the power n plus 1. So what we do is we take alpha to the power n plus beta to the power n plus alpha plus beta to the power n. That's what we compute. Now this would be minus p to the power n. This won't be positive. Okay. Now dividing by beta to the power n to this equation, we get alpha by beta to the power n plus 1 plus alpha by beta plus 1 to the power n is equal to 0. And if we divide by alpha to the power n, we get beta by alpha to the power n plus 1 plus beta by alpha plus 1 to the power n is equal to 0. So from these two equations, we see that alpha by beta and beta by alpha are the roots of the equation x to the power n plus 1 plus x plus 1 to the power n is equal to 0. Now we look at question 384, which says that if the roots of the equation x to the power 2 minus ax plus b is equal to 0 be real and differ by less than c, then show that b must lie between a square minus c square by 4 and a square by 4. So we let alpha beta are the roots of the given equation, and it is given that roots are real and differ. That means they are distinct. So the discriminant would be greater than 0. So we have a square minus 4b greater than 0, which implies that b is less than a square by 4. Also given that they differ by less than c. So mod of alpha minus beta would be less than c. We square both sides, we get alpha minus beta whole square less than c square. We replace this alpha minus beta whole square by alpha plus beta whole square minus 4 alpha beta less than c square. And we substitute for alpha plus beta whole square, which would be alpha plus beta whole square would be a square, and 4 alpha beta will be 4b, which will be less than c square. That is 4b greater than a square minus c square, and then we combine this, and we get the desired result. Question 385 says that let a, b and c be integers with a greater than 1 and let p be a prime number. Show that if ax square plus bx plus c is equal to p for two distinct integral values of x, then it cannot be equal to 2p for any integral value of x. So we are given that x square plus bx plus c minus p is equal to 0 for two integral value of x, which we take as alpha and beta. So alpha plus beta would be minus b by a, and alpha beta will be minus p by a. So we assume now that x square plus bx plus c minus 2p is equal to 0 is true for some integer k. Now once we have that, what we can do is we can rewrite this equation as k square minus alpha plus beta into k plus alpha beta is equal to p by a, which implies that k minus alpha into k minus beta is equal to an integer. So what we have done is we substitute x is equal to k over here. Okay, because that's what we take the root as. Now this k minus alpha into k minus beta is equal to p by a, but p is prime. So p by a will be an integer only if a is equal to p or a is equal to 1. But a is greater than 1, it is given, so it cannot be equal to 1. So a must be equal to p. That is a by p by a will be 1. So k minus alpha into k minus beta is equal to 1. But this is an integer. From here we deduce that it is an integer. That means k minus alpha and k minus beta both should be equal to 1, which is not possible because it will mean that alpha and beta are equal. But we are given that these are distinct integral values, so they are not the same. And that's how we have proven it, that it won't be equal to 2p. Question 386 says that if alpha and beta are the roots of the equation x square plus px plus q is equal to 0 and alpha to the power 4 beta to the power 4 are the roots of the equation x square minus rx plus s is equal to 0, show that the equation x square minus 4qx plus 2q square minus r is equal to 0 has real roots. So from the given equations, we say that alpha plus beta is equal to minus p, alpha beta is equal to q, alpha to the power 4 plus beta to the power 4 is equal to r, alpha to the power 4 into beta to the power 4 is equal to s. Now, the third equation is x square minus 4qx plus 2q square minus r. We let d be its discriminant, which will be equal to 16q square minus 4 into 2q square minus r, which will be equal to 8q square plus 4r. Now this is equal to 8 alpha square beta square plus 4 alpha to the power 4 beta to the power 4, which is equal to 4 into alpha square plus beta square whole square, which is greater than or equal to 0. So that's how the roots of the third equation are always real. Question 387 says that if alpha beta are the roots of the equation x square plus bx plus c is equal to 0, alpha 1 and minus beta are those of equation a1x square plus b1x plus c1 is equal to 0, show that alpha alpha 1 are the roots of the equation x square by b by a plus b1 by a1 plus x plus 1 by b by c plus b1 by c1 is equal to 0. So what we do here is we write alpha plus beta is equal to minus b by a and alpha beta as c by a. And alpha 1 minus beta would be minus b1 by a1 and minus alpha 1 beta would be c1 by a1. So we add alpha plus beta and alpha 1 minus beta. Beta gets cancelled. We have alpha plus alpha 1 is equal to minus b by a plus b1 by a1. And we divide alpha plus beta by alpha beta. We get 1 by beta plus 1 by alpha is equal to minus b by c. Similarly, we divide alpha 1 minus beta by alpha 1 beta. We get 1 by alpha 1. This should be minus. Okay. This should be minus alpha 1 beta. We get 1 by alpha 1 minus 1 by beta is equal to minus b1 by c1. Once we have that, we add these two. We get 1 by alpha plus 1 by alpha 1 is equal to minus b by c plus b1 by c1. Once we have that, we find the equation whose roots are alpha and alpha 1, which will be x square minus alpha plus alpha 1x plus alpha alpha 1. We divide the entire equation by minus of alpha plus alpha 1. We get x square by minus alpha plus alpha 1 plus x minus alpha alpha 1 by alpha plus alpha 1. And then we substitute the values of alpha plus alpha 1 and 1 by alpha plus 1 by alpha 1. And that's how we arrived at this equation. Now we come to the question number 388. How many quadratic equations are possible which remains unchanged when its roots are squared? So we let alpha beta be the roots of an equation which is given by x square plus px plus q is equal to 0. So alpha plus beta will be minus p and alpha beta will be q. So we now find the quadratic equation whose roots are alpha square and beta square. So that is x square minus alpha square plus beta square into x plus alpha square beta square. So the new equation would be x square minus p square minus 2q into x plus q square. How this we got is, we can write alpha square plus beta square as alpha plus beta whole square minus 2 alpha beta, and alpha beta is minus p, so alpha plus beta whole square is p square, and 2 alpha beta is 2q. But since the equation remains unchanged, the ratio of coefficient will be equal. Now ratio of x square will be 1 by 1, and for coefficient of x, p by p square minus 2q, and there should be a negative sign over here, and then q and q square. So these ratios should be equal. Once we have that, we solve this. Q is equal to q square, so q is 0, 1, and if q is 0, 1, p is 0 and minus 1, and if q is 1, then p is minus 2 and 1. So there are 4 combos or combinations, so we get 4 such quadratic equations. Question 389 says that if a, b, c are in GP, and then show that the equation x square plus 2bx plus c is equal to 0 and dx square plus 2ex plus f is equal to 0 have a common root if a by d, comma b by e, comma c by f are in HP. So what we do here is, we assume that d by a, e by b, f by c are in AP and a, b, c are in GP. We are given that a, b, c are in GP, so we assume the HP part. Okay. Now we'll see that whether our assumption is correct or not, and they will have a common root. So for the common root condition, we do the cross multiplication. We get 2 into bf minus cc by cd minus af is equal to cd minus af by 2 into ae minus bd. We cross multiply, we get 4 into bf minus cc into ae minus bd is equal to cd minus af whole square. We take bc common from the first and ab from the second. We get this equation. And from the right hand side, we take AC common. So you get this. Now, what we can do is, we can write as 4k into k into b square is equal to 4k square into AC, where k is the common difference of this AP. Okay. Once we have that, this is equal to b square is equal to AC, which means ABC are in GP, which was our assumption. So it turns out to be true. And that's how we have proven the required condition. Now we come to the last question of this set. Question 390 says that if the three equations a square plus x plus 12 is equal to 0, x square plus bx plus 15 is equal to 0, and x square plus a plus b into x plus 36 is equal to 0 have a common root, find AB and the roots of the equations. So we let alpha to be the common root and beta 1 be the other root of x square plus x plus 12, and beta 2 be another root of x square plus bx plus 15 is equal to 0, and beta 3 be a root of x square plus ab plus into x plus 36 is equal to 0. So alpha plus beta 1 will be minus a, alpha beta 1 will be 12, alpha plus beta 2 will be minus b, alpha beta 2 will be 15, alpha plus beta 3 is equal to minus a plus b, and alpha beta 3 is equal to 36. So once we have that, we can write that 2 alpha plus beta 1 plus beta 2 is equal to alpha plus beta 3, which implies that alpha is equal to beta 3 minus beta 1 minus beta 2. And we can also write that alpha into beta 3 minus beta 1 minus beta 2 is equal to 36 minus 12 minus 15, which is 9. So from these two equations, we can say that alpha square is equal to 9, so alpha is equal to plus minus 3. But alpha is greater than 0, so alpha is equal to 3, and beta 1 is equal to 4, 5, beta 2 is equal to 5, and beta 3 is equal to 12. So with this, we come to the end of the set. I hope you are enjoying this series and finding this video useful. So in the next set, we will see 10 more problems, that is problem number 391 to 400. And do not be constrained by what I teach. You can download the PDF and go ahead, and you need not necessarily wait for the video. If you have doubts, you can come to the video. There may be typing issues and you might get confused. So you can come and watch the video later also to get the clarification. So if you have any questions or you want to say something, please make use of the comments. So thanks a lot for watching the video. I wish you all the luck. Thank you. Bye.